speaker is Douthitt. He's going to talk about Chordal Matroids.
Thank you, Peter, and thank you to the organizers for putting this on. Thank you for inviting me. Before I really get going, I want to offer an open invitation to graduate students. Specifically, we have a weekly seminar we run at LSU that is simulcast, Zoom, and in person. So if you'd like to give a talk and put it on your CV as an invited talk, this is your invitation. It maybe is specific to North America, but if you're willing to make the time work for your time zone, we'd love to hear what you have to say. You'll notice there are two names on the slides here. One of them you almost assuredly recognize. The other is James Oxley. He's a math professor at LSU, I guess. So let's see what we have to say. Before I tell you anything about Matroids, I want to tell you what the graph kind of version of this is. So what is a chord? So I give you a cycle here in black, and then a chord is any edge that bisects that cycle, that is, has both of its vertices in the cycle, but the edge itself is not a member of the cycle. I'm not going to consider like a multi-edge as a chord. That would satisfy the definition I just gave, but I'm not going to consider multi-edges at all. Right? So with that, if I ever contract something, graph or matroid, I'm going to tack on a free simplification just with it. So if I say contract, it means contract and simplify. So what can we say about chords? A graph is chordal if every cycle of length at least 4 has a chord. Another way to say that is that graph is chordal if it has no member of C4, C5, or any longer cycle as an induced subgraph. If you're not familiar with induced subgraphs, this just means you're allowed to delete vertices. This is elegant because it's well controlled, but it's infinite. Right? It's elegant but infinite, and I don't like infinite. Infinite is uncomfortable. Sorry, Peter. But it's uncomfortable, right? So I want to do better, and I can do better by allowing contraction, right? So a graph is chordal if it has no C4 induced minor, and so now my operations are deleting vertices and contracting edges with simplification, right? And now I get one member, right? The contraction minimal member of that list. So what do we know about this? A graph is chordal if and only if it can be constructed from complete graphs by repeated clique unions. What's a clique union? I take two graphs, I identify a common complete graph in them, and I glue them together across that common complete graph. And I say clique union because I want to keep those edges in the gluing. Sometimes with a clique sum, this is a mod 2 sum, and so we delete the edges in the gluing. I want to really keep them. And I'm actually really excited to talk about this stuff here because at every other conference I've been to, I had to give the graph theory version of my research. And as you'll notice on this slide, Dirac did that in 1961. So not very new cutting edge stuff. So let's talk about kind of what happens as you go to matroids. So for graphs, our object is a complete graph. Our operation is clique union. Our substructure is induced subgraphs and induced minors. And so what happens for matroids? The complete object, there's some debate about this, but I firmly believe the complete object for matroids is projective geometries. Dimitri mentioned these yesterday. If you're not familiar with projective geometries, just keep your head back, eyes wide. I'll make sure to talk a little bit more about them. But the clique union is a bit more awkward. For graphs, we have vertices. They do so much bookkeeping for us. For matroids, we don't have that. And so we have to be a bit more careful, which means that the name is awkward, right? So the name for the clique union is a generalized parallel connection across a projective geometry. I do want to say with an asterisk here, this is not the only type of generalized parallel connection. There are more, but I'm trying to generalize the clique union, right? I want the complete object in the middle. Our substructures, we have induced restrictions. So we take a flat and we delete everything outside of our flat. That's allowable. And then we have induced minors. And so we take element contraction with simplification and restriction to flats. Okay, so back to Dirac. when you're doing a problem like this, you have a choice, right? You can take the construction and find the obstruction, or you can take the obstruction and find the construction. Here, the obstruction, chordal, there's some ambiguity in matroid theory what exactly that means, because again, we don't have the vertices, but this has been done for a while. And so I'm going to take the construction and find obstructions. So I define a class GFQ chordal matroids to be the matroids obtained from these GFQ projective geometries by repeated generalized parallel connection across projective geometries over GFQ. And kind of an observation here, due to Dylan Mayhew and Andrew Probert, is that this class actually gives you a saturated class of matroids and each of its members are supersolvable. If you don't know what those words mean, I can read the definition from Dylan's paper, but Dylan is here and may give you some better intuition about what those are specifically. Right, so here's our class. And what would you like, right? You'd like this class to be closed under some operation. And so one thing we showed is that it's closed under taking contractions. That's nice. And it's because you have this really beautiful structure of the two things glued together. There's really only two choices for where an element can come from. Either it's in the gluing middle part or it's on one side or the other, right? So there's loads of symmetry to be had. It's closed under taking induced restrictions. This is a bit more awkward because hyperplanes kind of wiggle around in this gluing. And those two together tell you it's closed under taking induced minors. Right? So we have a pretty nice class. And you get definitions like this. Right? So I want something that is just not in the class. Right? It's just the next one outside the class by any measure. So if I take a flat inside of it, I get back in the class. If I take a contraction from it, I get back in the class. That's all this says. It's quite wordy, but that's all it says. And so what are some obvious things to appear here? Well, if Q is 2, and we're in the binary setting, in rank 2, you have U22, which is 2 points. And that's actually the direct sum of two U11s, so that's in the class. And the only other option is 3 points on a line, and that's a projective geometry. Right? So in rank 2, you get nothing that's outside your class. In rank 3, you actually get something interesting. You get these two guys. I'm not going to go through how to get them, but you get them as, you can't build them this way. And they're really fundamental matroids. I think anyone who argues that is, well, just looking for an argument, I guess. When Q is bigger than 2, you get these guys, and this class is just the class of matroids. If you take 2 points and the line between them, either those 2 points are the only 2 points, or every point on the line between them is present. Right? So it tells you that your lines are either empty or full, essentially. And you get one more thing in rank 3, which is a bit awkward. It has to do with the representability of U3 Q plus 2. I'll talk some more about representability on the second to last slide. But if you contract anything from that guy, you'll get U2 Q plus 1, which means you just get in trouble, right? And this only happens if Q is even, because that matroid is not representable for Q odd. Okay, so here's our bad guys. And one thing that we showed is if you take a matroid that's not a projective geometry, and it has the property that any contraction from it is a projective geometry, then you get one of your bad guys. And I'm kind of throwing some stuff kind of behind the curtain, because there's lots of Q's to consider here. You have the binary case and the ternary case and so on. But in the binary case, you actually just get what are called Bose-Burton geometries, right? And if you think about these guys, this is a projective geometry. Delete a projective geometry, you're certainly going to have loads of 4 cycles in there, right? 4 circuits in there. Okay, I think this is the last definition. So a separation in a matroid is a partition. I listened to a talk of George Drummond, a student of Charles Simple, who kind of described this in a nice way, that you want to take two things that cover the entire matroid, but that their closures don't overlap too much. And that gave me more intuition than what Tut wrote, because, well, Tut wrote it. And so the nice thing about this definition is it's closed under duality. The not nice thing about this definition is it actually falls flat a lot. And so we need to extend this a little bit to a vertical separation. And all I've changed here is I've changed the minimum cardinality condition to be a minimal rank condition. And what this does is it takes away the awkward case when, say, a triangle, for example, it kills your high connectivity. Because if you have a triangle, that will be a separation. That, opposed to the rest of the matroid, will be a separation. But the cardinality of a triangle is 3. The rank of a triangle is 2. Right? So that's kind of the big differentiator between the two. Vertical connectivity, vertical separations are not closed under duality. But my class is not closed under duality. So this is OK for me. So let's take a 2 separation. And in my 2 separation, I want to take it such that each side of the separation is a member of my class. Let's see what happens, right? If P is present, I have a member, they join at a point that is present, and that's a parallel connection. So that's back in my class. Right? That's OK. If P is present, we're in the class, we're OK. If P is not present, then I want you to look at this and kind of squint your eyes, and you'll see that this is sort of like a line. This is sort of like a line, and you're getting the 4 circuit. Right? If you've got the 4 circuit, you've got U23, and so this is an obstruction to the case when Q equals 2. This is an obstruction to every other value of Q. So the 2 separation is, the vertical 2 separation is not a problem for us, and so we bump up the connectivity, and so now we have this thing, and this is 2 pieces again that are in my class, and they're meeting here. And one option is that where they meet is a projective geometry. And again, if it is a projective geometry, it's in my class, right? Because that's the operation. If it's not a projective geometry, then you're guaranteed to find one of your bad guys as an induced minor. And what this tells us is that if we have one of these barely not in our class matroids, it has no vertical K separations for any choice of K. And that's a round matroid. I'm not going to write another definition, but that's what's called a round matroid. A useful fact, I had this as a lemma, but after talking to the authors present, they agreed on useful fact. So useful fact, what we'll call it, is that if you have a round matroid, if you have this no vertical separation thing, and you contract anything, you still have no vertical K separations for any choice of K. And using that, we find that if you have a member of your class, of this class, with no vertical K separations, the only way this happens is that it is a projective geometry. And so it's actually one of your basic building blocks. And all of that together pretty much knocks off the problem. Obviously, I've hidden some stuff here from you, but and that's what you would hope for, right? The infinitely connected graphs or the complete graphs, the infinitely connected matroids certainly contain the projective geometries. And so we're able to write down this really nice characterization of this GF2 Chordal class, and this really extends Dirac's result by adding only one matroid. Right? It's the same construction Dirac gave, adds one matroid, and they're very fundamental matroids. In the case of Q is bigger than 2, we get exactly those matroids that we wanted. Again, this guy over here drops off the list should you take an odd Q. And this is kind of where the story ended. We finished it, we published it, and I gave a talk, and Jagdeep Singh asked, can you do this for induced restrictions? And I said, that sounds really hard. And I met with James, and he said, yeah, I agree, but go away and do that. And so I went away, and well, what can we say about induced restrictions? Right, so if you have a 4 circuit as an induced minor, then you certainly have some longer circuit as an induced restriction. And you can just take that, the one direction of this is immediate, the other one takes a bit of work. But this gives you a nice relation between the two, and it is exactly this class of chordal graphs. Well, it contains it at least. It's the same relation. And so now if I don't want MC4 or MK4 as an induced minor, well, I'm certainly going to have the list from the lemma above. That's certainly going to be there. I'm certainly going to have K4 because it's in the previous thing. And the hope is that this list doesn't grow a lot. Right? The hope is that maybe you get, best case scenario, you get one more thing. Worst case scenario, you get all complete graphs or something nicely controllable like this. But we actually get one more matroid, and it's M star K33. And it's quite elegant. So how do we prove something in this domain? I was told if you have a proof that includes the name Tut and the name Seymour, you should probably talk about it, because those are some big names. So what I want to do here is I want to assume that I can contract something from my matroid and get to m of k4. And one really immediate observation is that the size of the ground set is very bounded. This is a really lazy bound. 7 comes from the fact that that's 6 plus 1. You contract something and get k4. 15 comes from the fact that you're in rank 4, and that's the maximum number of elements there. Some fairly straightforward case analysis can rule this down to saying you have fewer than 10 elements. If you think about taking a rank 4 projective geometry and delete just a few points, you're definitely going to have K4 or the 4 circuit as a restriction in there, right? Because, I mean, you just have to. So M is 3 connected. You can think of the same picture I showed you a moment ago. If it's not 3 connected, it has a 2 separation. That means it meets at a point. If the point's missing, it's got C4. If the point's present, well, K4 is 3 connected, so that means it's got to be actually contained on one side already. M is not graphic. If it is graphic, it lives inside of K5. You can make some arguments about how you can delete edges from that, but it's not graphic. So we get to a result of Tut. This is the characterization of non-graphic matroids. So if we had K5 as a minor, well, M star of K5 has 10 elements. I think bullet point number 2 rules that out. M star K33 is on our list, and the other two kind of get gobbled up by some Seymour stuff. Right? So using some results of Seymour, we extend the Fano dual in rank 4, and we don't grow a lot, right? There's only a few elements you can add, and there's only a few ways you can add those elements. And so this last bullet point's actually just looking at 5 total matroids. And each of them has one of those 3 bad guys as an induced restriction. Right, so in the binary case, what we can say is that matroid is GF2 chordal if and only if it has neither MK4 nor MC4 as an induced minor, if and only if it has no member of this other list as an induced restriction. And I think this is maybe the most elegant thing I've ever proved personally, because these are, if you had to list the five of the most fundamental matroids, I think 3 of them are on the screen right now. And I just think that's really, really attractive. Binary is great, right? Non-binary, not so great. And so we need to consult a paper of Simeon Ball. I think this paper was available as early as 2008. In Oxley, it's in 2010 is when the citation is. And I think the journal article was actually 2012. So I averaged them and did what James said. So 2010 is what we write, but it gives us a characterization of what uniform matroids are GFP representable when P is a prime. And using this, we can say something, while albeit unattractive, you can say something about the GFP case, GFP chordal case. So the first 2 bullet points are kind of from the first bit of the talk. The last one here, we add this guy. This is just circuits. And these are regular, so they're going to appear everywhere. And this is just kind of co-extending the members of this class one at a time until you're no longer GFP representable. And so it's not really saying a lot, but it seemed like some kind of a completion. For the sake of completion, we need to include this. Any questions about the math part of this talk before I stop with the math part of the talk? No? Okay. How much time do I have, Peter? 5 minutes? Okay. So I want to say thank you to IBS and Sangil. Everyone here has been so gracious to me and my entire cohort. I don't know who made this thing, maybe Rudker. I thought this was incredible. If anyone doesn't know, these are all things around Daejeon. And it spells sigma. And when I saw this initially, I recognized this one, obviously, and this one, obviously, and this is just kind of something you see a lot in Korea. This one I didn't recognize. This one I thought was something else. But I asked Rutger what they all were, and I went around and I collected each of these photos to recreate this image specifically as a gift to Rutger, but I thought I would share it for all of you and just my appreciation to IBS as a whole. And here's some other pictures that I just think are really pretty. So thank you for your attention.
I'm not so sure about the bottom right one.
I think the bottom right one is maybe the great. You can see how much math they're talking about. Like these guys, it's so beautiful all around them, and they're just nerding out about math. Like, look up, come on.
Are there any questions for Dylan?
So the Chordal graphs have a lot of nice properties in graph theory. So I wonder whether some of them can be extended to like matroid, like perfectness or whatever.
So every time, I actually almost included another slide after this to say, are these perfect? I don't know. Because every time I've given this talk, the number one question is, are these examples of perfect matroid? Well, I think perfect matroids are maybe somewhat ambiguous in the literature. I'm not exactly sure. But there are others. There's a characterization of perfect elimination orderings that we do actually pick up with this class. And we've tried a few other, there's, I think, maybe 10 characterizations of chordal graphs. And we've tried seeing if it aligns with some of these, and not so lucky with some of the others.
Are there any other questions?
Yep, Dongyu?
Can you consider something similar about the Dowling geometry rather than the projective geometry?
I'm sorry?
Dowling geometry.
Dowling geometries?
Yeah.
I haven't tried this at all with Dowling geometries. They kind of scare me. There's some bit of... with projective geometries, you can match them up really nicely. With Dowling geometries, there's some awkwardness about making sure you're consistent when you put them together. And it just seemed a bit awkward to me personally. And as much as it maybe frustrates James, I think a lot more geometrically than graphically. And the Dowling geometry feels, I guess, more graphic than geometric.
Are there any other questions?
Okay, if there's no other questions, I do want to take a photo for James. So if any of you feel connected to James or would like to be in a photo to send James well wishes since he is not here, I would like to take a photo just before the coffee now. So if you could come kind of this way. Anyone who wants to be in the photo is welcome. There will be a conference photo, but this is specifically an Oxley moron photo, I guess. So if you would like to be in a photo for James, he would very much, I think, appreciate just seeing all of our faces and whatnot.
So actually, did we thank Dylan again?